So microscopy, right? So as we said, right, most of the microorganisms, you're not going to see them unless they grow in huge numbers in that apple juice. We need a microscope. And are there different types of microscopes? Oh Lord, is there a lot of different types of microscopes, right? But the main reasons why we use microscopes are these main principles, right? Is to be able to magnify it so you can actually see it, right? Sometimes the microscope can help us with contrast. Other times we'll need to stain to create contrast, to be able to differentiate it from its environment, from its surroundings. Resolution, how clear we can see that image, is really dependent on what the type of tool we're using, what type of microscope we're using. And especially with light microscopes, that resolution is really dependent on how good that lens is used by those microscopes. And that ability of that lens to capture light, and that can be mathematically calculated. It's referred to as the numerical aperture. And so just like for your lenses, for people who need corrective lenses for glasses, you have a prescription, right, that lets them know how to make that lens to correct for the lens in your eye that's not working properly for what you need to see, right, to be able to see it clearly. And then, especially again with light, we have to deal with refraction of that light. And different substances have different refractions of that light, which again can be referred to as the refraction index. So we'll look at each one of these and talk about their importance as it relates to microscopy. The magnification is pretty simplistic, right? We don't actually make the organism bigger, right? The image appears larger, so we're able to visualize it easier with the natural lenses in our eyes. So we use additional lenses, or in the case of an electron microscope, right, the use of electrons and a computer to be able to interpret those electrons and the difference in movement based on the different things that it's passing through. So it wasn't actually until the advent of the electron microscope that we could see some of the much smaller things like viruses, right? Viruses you're not going to see with a light microscope. But we could see bacteria, right, as we do in the microbiology lab, and large eukaryotic organisms like amoeba, and even our own cells, our red blood cells and white blood cells. Did I show you guys this size website last time? Okay, right, so you guys have seen this one. And then we have even more powerful atomic force microscopes, scanning tunneling microscopes, that again, we're using atomic force in a computer to calculate what is actually being seen. But they can go right down to the atomic level and discern different atoms from one another and their relationship in molecules. Pretty amazing stuff. I've never worked with those because they're relatively new since I have started teaching. So unfortunately, when I was in school and doing research, we didn't have access to those type, not readily anyways. Who knows, maybe I'll get to do a sabbatical, right, and go check out these new microscopes. So this magnification, right, is an enlargement only in appearance, right, not in physical size. So things like this bacterial phage, this virus that infects bacteria, right, this is an electron micrograph. And for the most part, again, it's going to be shades of gray that show the, the different structures. And you'll notice here, this is a size meter, right? So this line represents 100 nanometers. Right, so it's teeny tiny. Here's a bacteria, and you can see flagella and little fimbriae that we're going to talk about next time. And this one, it's a particular preparation where they've kind of etched away the different layers, so you can actually see, the outer layer, the outer membrane. You can see the cytoplasm, the plasma membrane of this probably gram-negative cell. If you see color associated with electron micrographs, it's because someone's colored it. So you guys remember like the old black and white images, and then they would go in and literally physically paint and color on them? The same thing can happen here, right, where they can generate this black and white image, and then they can add color, you know, to help with people understanding what they're looking at in the image. So bacteria in general are transparent, right? Some of them have pigmentation to them, but a lot of them don't. So in order to see them, a lot of times we stain them. And some of the stains that we do actually tell us more information other than what you see here of all these different shapes and colors. The different colors actually mean something. So like we'll talk about in the gram stain, if they come out purple, they're said to be what's called gram positive. And that's an important distinction for bacteria. It tells us something about their structure. And then gram negatives, this tells us something about their structure as well. When they're saying positive and negative here, it's almost like when you run a pregnancy test, right? Either you're pregnant or you're not. When you run a gram stain, you're either purple or you're not, right? So if you're purple, you're positive for this test, for the gram stain. If you're pink, you're negative for the gram stain. And again, this correlates to information about the cells. So there's a reason why we do this particular staining procedure. Same thing with acid fast. You either are acid fast or you're not. They don't say positive and negative typically with this. They say acid fast or non-acid fast. And we can actually stain those endospores, right? Those heat-resistant forms of the bacteria, and you can see them as little pink dots here. And then you can see the bacteria themselves. These are more complex staining procedures where you're using multiple dyes. These staining procedures are referred to as simple stains because you're using just one dye, and again, typically just to be able to see the shape of the organisms and actually see them. Whenever you dye a bacteria, you're going to kill it, for the most part. In this case here, the bacteria are actually not dyed. You see the cells? Right here and right here and right here. The background is stained instead. This is a different staining type of stain. It's referred to as negative staining because it's almost like a picture negative, right? Where it's opposite than what you would see on the paper. So contrast, very simply, is the difference in color and light between the parts of an image, right? That help us discern and differentiate what we're looking at. Resolution, on the other hand, is the ability of a microscope to separate or distinguish between small objects that are close together. But it also factors into how clearly you see the objects that you're looking at. So you'll see these three pictures are all of a euglena, right? A little protus that has chloroplast, so he's naturally has his own kind of pigmentation to him because of the pigments for photosynthesis. And that's why you see this color in here, that's his chloroplast. This is bright field microscopy. This is what we do in the microbiology lab where everything is bright, right? The light is shined and everything is bright, and it's stuff that's stained or has natural pigmentation will absorb the light and you'll see it differently. This is dark field microscopy where the light is shined at an angle. So the background, as you can see, is dark, but the organism itself is illuminated, right? You can see how it's kind of glowing. The bottom picture is using a microscope that creates contrast by changing the wavelengths of the light out of phase with each other. So it's called phase contrast. And you can actually take a light microscope and add these special filters to it and make it a phase contrast microscope. And then when you really look at this one, you're like, wow, look, there's more than just that euglena there, right? Do you guys see? All the little things outside? That's more little organisms on that slide that you really couldn't see, right? You couldn't discern them because of either a contrast issue or a resolution issue or really both. So resolution, or the limit of resolution or resolving power, can actually be calculated if you know certain factors. And so this number that we get is the minimum distance that two objects need to be apart in order for you to see them as being separate. So in order to do that, you'd have to know the wavelength of light that you're using. And a lot of times we use filters, blue filters, or around 500 nanometers for our microscopes. It's the smallest wavelength of light, so therefore it's going to give us the best image because it's going to give us the smallest resolution number, right? So we can put things really close together. Makisha, do you need those glasses to see me? To see the board? Okay. Can you take them off for a second? How many fingers? One. Okay, put your glasses back on.
I thought I was...
Right, because actually we use other things other than our eyes, by the way, for vision, right? So she's calculating, like, how thick would her fingers be? Is that 1? Is that 2? Right? Because for her, they're not as clear for as they are for the rest of you guys that you're like, oh, it's 2, right? And what's the problem is they're close together. If I went like that, she would probably say 2, right? Without her glasses, depending, right, on her prescription and how much her natural lenses aren't allowing her to see. Does that make sense to you guys? So we could calculate this. We know the wavelength of light, and you know the prescription, say, for those lenses, that numerical aperture for the lenses that are on that microscope. You could use this formula and you could calculate that distance. So you know how close you could put them together and someone would see them as being separate and when you wouldn't. The good news is you guys are in lecture class. We don't deal with the math stuff in lecture. In lab, you got to know this, right? In this, you just got to understand it. So that numerical aperture, that prescription you could say for each lens, is always right next to the magnification. So magnification is always times x, right? So 10x for this lens, the slash, and then the 0.4, that's its numerical aperture. And you'll notice each one of them has a different number, right? This objective lens is 0.7. This one is, I think, 0.85. Yeah, because that's a high dry. The 40x are typically 0.85. It's kind of ridiculous that I had that memorized, but I do. When you repeat things over and over again, you can't help but to remember them. Right, so we would use that, right, and the condenser is actually the lens in the stage, right, that focuses lights onto the specimen. So that one's important too. How good is it focusing the light onto the specimen? And then how good are these objective lenses at focusing the light in and up so that you can see what you're looking at? So the property of a microscope lens that determines how much light, right, can enter and how great the resolution that lens can provide. So another problem we run into with light is refraction. So is that pencil broken? No, but it appears to be displaced, does it not? What's the problem? It's in what? It's in two different medias. It's in water and air. It moves, I want to say slower through water. Doesn't matter the speed. It's different though, right? It's different. So this creates a problem for us as far as microscopes go. And fishermen, right? Because if you're trying to spear fish and you're not in the water with the fish, you run into that same problem, right? Just like this is displaced, so are the fish, right? So the actual position of the fish is here, but you think it's right here. So you try to stab it, you're going to miss every time. Not to mention the fact that it's probably moving, right? So refractive index is the measure of the relative velocity, right, the speed, as it passes through the media. But this affects how we see it, right, and where we see it. So one of the lenses that we use gets really close to our slide, or our slide with a cover slip in this case, in this drawing. So much so that because it's going through glass, the light, and then through air, some of it gets refracted and it doesn't actually make it into the lens. So notice on this side, right, only about 2 rays of this light is actually getting in. On this side, oil, what we call immersion oil, has been applied to the slide. This oil fills the gap between the lens and the slide, or the cover slip in the slide. This helps focus the light because this immersion oil has the same refractive, or very similar refractive index to glass. So it just keeps, the light rays just keep traveling at the same speed, right, and keep going directly into the lens. A lot of times in microbiology lab, students are like, Miss Erica, I can't see. I'm like, yep, I know, you're not in focus. How do you know? I'm like, because I see a big gap between your oil objective lens and your slide, and I shouldn't. I should see a little tiny gap, and oil should be filling it. If there's a big gap, you're not seeing anything, right? You gotta go back to low and start over, right? Get it focused at low power, and then go back to oil, right? And a lot of times students like get freaked out because they're like, oh my God, it's so close. And I'm like, if you're in focus at low, really, you'll be okay. It won't smash into the slide. So this helps too, but also, you know, think about this too as we go to the higher magnifications in this case, less light is getting through altogether. And so sometimes some students at the lower magnifications decrease their light, whether that's the iris diaphragm in the condenser or the light intensity wheel on the microscope. And then when you get to oil immersion, you can't see anything because it's too dark. You just got to let more light in, right? Open up the iris diaphragm, increase the light intensity, and then woo, wow, the world is beautiful, right? Light's important though for vision, right? And it's also a limiting factor though for us, right? Because our eyes can only see within the visible light spectrum. You can't see ultraviolet light, can you? No, not unless something fluoresces it, right? Some things you expose to UV light and it fluoresces, you can see that because that falls into the visible light spectrum. And so there are special microscopes that you can use fluorescence that utilize UV light. And again, those have to have special filters on them because you don't want to damage your eyes either, right? UV light is damaging. It causes mutation in your DNA, right? This is why you want to protect yourself from sunlight, right? I always tell my students all the time, I'm like, don't do the tanning beds, y'all. That's just crazy. I mean, you're just asking for cancer faster than the rest of us. If any of you guys know Dean Gruber, the head of our division, have you seen his nose? Yeah, that's cancer. It was cut off like 2 times or so. He was like my dad, baseball coach, outside in the sun all the time. Never wore protection. What did I do to me and my son before we went to the zoo today? We lathered up in the good old sunscreen because we're both fair-skinned, and I don't want to have skin cancer. Yeah, I haven't used water immersion, but there are some, and I would love to like get to do that because the oil is so messy. And when you don't clean the oil off the scopes, it creeps in and causes the lens to be blurry permanently, which is the case for most of our high dries because students don't follow instructions.
So then why is the, like, is it just like the microscopes out there?
Yeah, we just, we don't have the ones that can do the water at this time. Yeah, I know, I've heard of it. One of my friends, he's like, yeah, we need to do this. And I'm like, yeah, we need to find the money to do this. But again, you know, as things change, I mean, it will probably get to that at some point. I was laughing because when Prince died, one of my friends took out her Purple Rain record. And it's purple. And her son goes, how are you going to play that CD, Mommy? It's too big. It's a record. He'd never seen a record before. So, you know, I mean, it just takes time. Yeah. You know, it just takes time. But yeah, again, the whole purpose is to try and just get that light where we need it to be able to visualize. And if we could do that with water, which isn't as messy as oil, that would be great. But you have to have special lenses for that. So with really cool microscopes, you can see really cool things like this amoeba. It looks like he's going to get you, huh? Looks like the blob, right? It also even looks three-dimensional, right? This is a difference in inference phase contrast microscope. And these are really cool because, again, they can create contrast without staining the organisms, so you could actually look at them alive and moving. So if you are a YouTuber, right, there's tons of videos out there, right, using cool microscopes like this where you can see the cilia on the paramecium, and you can see them moving, and it's really cool. Amoeba too. And then, like I said, fluorescent, some organisms are fluorescent. The use of fluorescent dyes, and even specific fluorescent dyes with antibodies attached to them where they only stick to certain things, have really advanced the different things that we can test for. And in this case, like a specific antibody that binds to Streptococcus prurigens, right? So if they're, do a slide, and does anybody know what Streptococcus prurigen causes? Strep throat, right? So that's where it gets its name. It's actually from the organism that causes the infection. And they're cocci in chains, so you can see that on the microscope, right? So these are little circles that form chains. And that's what Streptococcus means, chains of spherical bacteria. Again, electron micrographs, and some of them too, you can actually have somewhat three-dimensional. These are referred to as scanning electron microscopes. They're really cool. This particular microscope uses lasers. So I got to observe a researcher use this at LSU vet school. This, you won't find this microscope there. Like, someone has to take you there. You have to walk through 2 labs and then into a small room to get to it. It has its own air conditioner in there too because of the lasers. It gets really hot. Its own computer, and they can generate on the computer, right? They can scan, you know, layer after layer with that laser and generate these 3D images on the computer. It's pretty amazing stuff. And then with special dyes, you could see, you know, the different parts of the cells and everything. It's pretty amazing stuff. And then this is the scanning tunneling, and again, they're using atomic force. And the colors here are just to denote the differences, and this is DNA, right? You can see the double helix there. So right down to the molecular level, you can see things, you know, pores on the surface of a cell in the membrane, how the proteins are arranged. So why do we use the staining procedures? Right, so for simple staining, we're just using one dye, right? And we just want to see the organisms, right? We want to see their shape or how they're arranged. But with gram stain and acid fast and endospore, as I said earlier, this is going to tell us a little bit more about the organisms, because these are multi-step procedures that use multiple dyes and reagents. The capsule stain and the flagella stain, as the name implies, the capsule stain we do in order to visualize a capsule if it's present. The flagella stain we do to be able to visualize what? The flagella. That's a no-brainer, right? So what's a simple stain? What do we use? One dye. Why do we stain the cells? To see them. So there are 2 different types of dyes typically used. Ones that are referred to as basic dyes, and others are acidic. So basic dyes have a positive charge. Anyone want to guess what charge your cells have, or cells have? A negative charge. Because what do we know about opposites? They attract. That explains my first husband. Right? So if cells are negatively charged and basic dyes are positively charged, they're attracted to each other, right? So then you see images like you see here, right? Because crystal violet and methylene blue are basic dyes. They actually go inside the cell or even coat the outside of the cell because they're attracted to those negative components of the cell. Your membranes typically tend to be negatively charged, so do all cells. And inside that cell, you have a molecule that's highly negatively charged, which is very important to the genetic makeup of your cells. What is that molecule? DNA. And that's why, again, for eukaryotic cells, the nucleus stains so brightly. That's because it's extremely highly negatively charged because there's a whole bunch of DNA in there. Where the cytoplasm, not so much, right? But the membrane, too, will usually get stained. Right, so when you're looking in A&P lab and you're looking at those beautiful cells under the microscope, that's why, right, you can see it so clearly, the nucleus, usually in the cell membranes. Because they're negatively charged, and they're usually using a basic dye. Those are the most commonly used dyes because of that charge. Now, in contrast, acidic dyes will probably have what charge? Negative. So are they going to be attracted to the cell? No, they're going to be repelled by the cell. So you'll see something like this image here. You'll get a negative staining, where the background gets stained and the cells do not, usually. Sometimes they'll get a little stained, but for the most part, just the background, because those like charges, negative and negative, repel each other. So what do we see? What can you tell me about these organisms because we stain them? Like, you know, you're Anthony von Leeuwenhoek, and you're looking at this, right? And you're telling the artist what to draw, right? What are you going to tell him to draw? Yeah, but you've got to describe it. He can't see it. Huh? The structure of it. So what does it look like to you guys? What does it look like? Give me something, right? I'm the artist, right? Imagine I'm like that crime sketch artist, and you got to tell me what the bad guy looks like, right? So what does that bacteria look like to you? Use something you know in your own everyday life. What does it look like to you in your own everyday life that I would know? It looks like a worm. Okay, that's good. You're getting warmer. It looks like a green bean. Good. Keep going. You guys can think of better stuff. I see sausages. Do you guys see sausages? Yeah, come on. You can say it. We're all friends here. Right? Again, you know, these are important things, right? Being able to describe what you're looking at, draw what you're looking at, right? Communicate that in some way that the people that you're talking to are going to understand you. But these are important because do all bacteria have this shape? No, some have different shapes, and this is an arrangement. Notice these are actually two right next to each other. This is what we call diploid, right? Two, or pairs. And that's important because some of them always characteristically form these pairs. Or in the case of streptococci, they always form those chains. And this helps in identifying an organism if you don't know what it is. Now, differential stains, on the other hand, as the name implies, helps us differentiate. So we're going to see differences. In this case, what are the differences you see here? So in this picture, what do you see? You see purple and pink, right? So again, when we do a gram stain, it's going to be, is it purple or is it pink? And what does this tell us, though? For acid fast, do you see these kind of purplish pink ones and then you see kind of blue? Right? Those are different cells. They stained differently in the acid fast stain. So can we still see shape and arrangement? But we also get more information, right? We're getting a different color. This tells us, based on the procedure, more information about the cells. We can actually differentiate the cell from the endospore. The endospore has a different color. So for acid-fast staining, this isn't as widely used as the gram stain because one genus of bacteria stains acid-fast, and that's mycobacteria. And that's because they contain a substance known as mycolic acid in their cell walls. And this allows the carbofusion, the dye, that even when we decolorize with acid alcohol, that's where it gets this name of acid fast, these guys do not lose that color. It stays. So in this case, when we say fast, we're meaning it stays put. Fastidious. It's not going anywhere. The other cells get decolorized and you see them as whatever it is that you're using as your counter stain. In this case, it's probably something like methylene blue because they're blue. Different staining methods out there for acid fast staining though. So that's important too, right? When scientists do acid fast staining, they actually indicate which method they use. Same thing for endospores, right? There are different methods out there, so the scientists would say what method they use, and this would, of course, help them determine what color means what for what they're looking at. So as we already said, these are easy, right? The stain tells you what you're looking for, right? Capsule stain, we're looking for capsules. Flagella stain, we're looking for flagella. Why do we need these special stains to see these structures? So with the capsule stain, and this is actually yeast, but bacteria produce capsules too. So right here in the center, it's barely stained. You can see that little circle. That's the yeast cell. And this area here that's clear is the capsule. And then here is the background that's been stained. So they use an acidic dye. They stain the background. And a lot of times they use another dye and they'll stain the cell, especially for bacteria, so we can really see that cell. The capsule, on the other hand, does not have a charge, so it doesn't stain. Because that would make it easy, right? It'd be a one-step procedure. We could just have a special stain, and we'd just stain the capsule, and we'd be done with it, right? No. Instead, we got to stain the background, we got to stain the cell, because guess where the capsule's located? Here's the cell. This is outside the cell, right? So if we stain the cell, would you see the capsule? No. If we stain the background, would you see the capsule? No, we got to stain them both, right? The cell and the background. And then in between, if it's there, you see the unstained capsule. Little trickery there. You still with me? Okay, that's the tricky one. Okay, flagella, so this is actually a bacteria. The bacteria, by the way, of our light microscope, they're about the size of the limit of resolution of our microscopes. So we just about, right, see them as separate cells. That's it. Their flagella are smaller than them. So again, imagine on our body, right, our hairs, how thin they are in comparison to our whole body. So think about that. So now a bacteria, right, you're trying to see basically his little hairs. Well, you're having trouble enough seeing him, never mind the submicroscopic hairs. Ain't gonna happen. So what we do is the stains that we use for this bind to the flagella. So they kind of coat it. And probably the best analogy is mascara, right? We add mascara to the lashes, right? And so you're painting them, so if they're light colored you can see them, but you also will add thickness to them. So it's like sticking mascara on them. When you do that, when you make it thicker, it's easier to actually be able to see it under the microscope. So do you think they're still alive when we do this? No, because all staining does what? Kills them. So you can see when they were alive that they were moving around because, look at this guy, he's like Scary Cousin It from the Addams Family. He's covered in flagella. I mean, he's just covered all over. Proteus vulgaris. He smells vulgar too. That's probably how he got his name. E. coli's like this too, though. He's just covered in flagella. Just covered in it. So he can really motor. Next thing we're going to talk about is probably one of the paramount procedures in microbiology, It's the gram stain. It's the one thing, if you leave this class and you don't know, you will see me cry. Right? I'm not ever going to shut up about it for the rest of the semester, or the summer in this case, session. It is that important. It is paramount to a lot of what we know and understand, and even how we treat infections. Because if we know our enemy, we can defeat them, right? And when it comes to bacteria especially, knowing what they're made of will help us destroy them, if that's our goal. Which a lot of times it is when we're talking about medicine, right? Someone's got a bacterial infection, right? How do we eliminate this particular bacteria? Well, we got to know something about it, right? One of the things that we can know about it is do a gram stain, and it will tell us about its cell wall structure. And that's going to affect how we can attack it, right? If he's really fortified, he's got layer after layer, we're going to have to get past all those layers, right, to attack and kill him. But if you only got one big thick layer, probably going to be a little bit easier to defeat that bad guy, right? The same is true here. Doing this procedure lets us know, do we have one wall we got to breach, or do we have two walls we've got to breach? So I'm going to go ahead and play this YouTube. This is an animation from the textbook, but you know, everything's on YouTube nowadays, and it's easier and better to always access, as long as you have internet, stuff on YouTube. So I just went ahead and saved that YouTube, which I clicked on earlier. And where is it? There we go. We'll make it big screen. You guys want to, I'm hearing someone else. You guys want to go ahead and close the door, especially since I'm going to play this, and I don't know how good the audio is going to be. Thank you. All right. No, you don't need it. It's got pretty good resolution. So those of you guys in lab will actually do this next week. So let's see. I always got to remember to hit the correct button. That's for my recording. This is for playing the video.
The gram stain is the most widely employed staining method in microbiology. It is a differential stain because it divides bacteria into two classes, gram-positive and gram-negative. In the first step of the gram stain procedure, cells from a fresh culture are transferred to a clean slide and allowed to dry. If the cells are on an agar plate, they should first be transferred to a liquid medium for dilution. The cells should form a thin, barely visible film. This can be achieved by smearing cells obtained from the surface of an agar medium or from a liquid culture. Fresh cultures must be used because as cells age, they lose their ability to retain the stain. The cells are then fixed to the slide by passing slightly above the flame of a Bunsen burner. After passing above the flame, the slide should feel warm when touched to the back of the hand, but should not be too hot. The fixed cells are then stained with the basic dye, crystal violet, for 30 to 40 seconds. The slide is then rinsed with water to remove excess stain. At this point, all cells appear purple under the microscope. Next, a solution of Grant's iodine is added and retained on the slide for about 1 minute. The iodine combines with the crystal violet to form a di-iodine complex, thereby decreasing its solubility within the cell. At this point, the cells still appear purple. The cells are then decolorized by washing with ethanol or acetone. This is the differential step. Gram-positive bacteria retain the crystal violet, whereas gram-negative bacteria do not. The ethanol or acetone should be added drop-wise, with the slide tilted at an angle until the drop coming off the edge of the slide just starts to become colorless. Even gram-positive cells can lose the crystal violet iodine complex during prolonged excessive decoloration. Excess ethanol is then washed off with water. When viewed under the microscope, gram-positive cells appear purple and gram-negative cells are colorless. Finally, the rinsed cells are covered with the counterstain saffronin, for 20 to 30 seconds. This stains the gram-negative bacteria pink. After rinsing with water, the slide is dried with filter paper. When viewed microscopically, the gram-positive bacteria are purple and the gram-negative bacteria are pink. Generally, the gram stain correlates with the cell wall structure among the bacteria. The ethanol is thought to shrink the thick peptidoglycan in gram-positive cells, thus retaining the dye. The thick dehydrated peptidoglycan layer of gram-positive bacteria appears to be a permeability barrier, preventing the loss of the crystal violet iodine complex. In contrast, the peptidoglycan in gram-negative bacteria is very thin and has large pores. Ethanol may extract lipids and increase the porosity, thus removing the crystal violet iodine complex.
That's a lot, huh? We're going to go step by step. Okay, so this other guy, she's cool, by the way. She's got a lot of microbiology videos. I stopped making some of them and just told my students to watch her. Let's see, I don't want this to accidentally play on me. So this other one, I gotta be in presentation mode to click on it. There we go. It's warning me that I'm going elsewhere. Okay. I need to thank this guy because this one's awesome. Two guys, Danny and Mark, at North Carolina State. This one doesn't have any audio though, so we'll provide our own. So what's the steps? Crystal violet, iodine, decolorize, and we use alcohol because acetone is damaging to mucous membranes, right, ladies? Yeah, we try not to use that stuff. But we do for our nails, right, to remove that paint. And then we counterstain with safranin, right? That order is very important, as you will see. And then we saw, right, you get two different cell wall structures. As I said, do we have one barrier or do we have two? This tells us. So let's start with the one guy, right? And that would be our gram-positive. And again, positive and negative doesn't mean charge or anything like that. This is basically a test you're running. Does it stay purple? Okay, it's positive. Does it not stay purple and therefore pink? It's negative for the gram stain test. Okay? So let's start with our positives. So for a cell, all cells are going to have a membrane, right? And that's represented here, right? We have our phospholipids. Oh, where's the ID menu? There we go. Right? So our phospholipid, our embedded proteins. Here is teichoic acid that's associated with the cell wall, right? And then we have the peptidoglycan layer, which we know is unique to what domain of organisms? Bacteria, which is what we're talking about, right? Crystal violet iodine complex, we're going to see decolorizer. I stands for iodine, S for the safranin, and C for crystal violet. So, and of course it does have written out script too. So the first thing we do is add crystal violet. And remember, this is positively charged dye. It's a basic dye. So where is it going to go? It's going to go inside. It's going to be attracted to these teichoic acids too, but it's also going to go inside because remember it's heading towards what? The DNA, right? It's heading towards that DNA, which isn't even in an envelope or a membrane, right? Because this is a prokaryote. But it's in there. It's in the cytoplasm, right? And kind of in its own region. So that crystal violet is just being drawn to that DNA. So it's going to go in the cell. So there it goes. In it goes. Then we're going to add the iodine. It's going to go in. And crystal violet usually complexes with chlorine ions. And in this case, it does a little switcheroo. He's like, okay, I don't want my chlorine anymore. I'll take some iodine, right? And the difference here is that now you have crystal violet and iodine. And so you have two molecules coming together, right? So now it's bigger. It's a complex, right? It's bigger than the two that came in separately, that crystal violet and that iodine. So they bind with each other, and It's a bigger molecule. And that's important, right? Because bigger things, it's harder for them to get back out, right? So then the decolorization step. So who was paying attention? What does this do to the peptidoglycan layer? Thins it kind of. They believe it, watch. What did you say that was? Shrinks it. Right? Alcohol does strange things to things, right? If you use too much hand sanitizer, what happens to your hands? They dry out, right? Because as we'll see in a moment too, it's really good at dissolving lipids, right? And so again, the fats and the stuff that keep you moist, you're removing that when you use too much alcohol. Or in the case of me lately, just washing my hands like crazy. Like the intense moisturizers on my desk. And that's also why a lot of the hand sanitizers are like trying to put moisturizers in it so that people will continue to use it despite that it dries it out. But that's also something to take into consideration as you watch this, right? Which cells is this going to affect? Gram-positive or gram-negative? Right? Which one is it damaging the most when you use that ethanol hand sanitizer? Okay. So complex shrunk, right? So notice there were spaces in between these molecules, right? And they just got what? Smaller. And we have a bigger molecule on the inside. So is he going to get out? No, he's trapped. It's like, oh, I'm stuck. I'll have to stay in. Right? So these cells at decolorization, if you don't do it too long, they're going to stay purple. So what's the last step? Safranin, right? Is that going to go in? Well, it's another positively charged dye, so he's attracted. He's going after that DNA. He's going to go right in. So why don't these cells look red instead of purple? I'm going to pick on Kat. You have that beautiful dyed hair, right? Yeah. So, you ever done laundry? Or messed with dyes, right? If we dyed her hair pink, right? And then we come back over it, we could do the purple and the blue. But could you start out with the blue and then try and turn it purple? No, because the purple's brighter, right? So like when I was a kid, I accidentally, like my family was so big we could divide into color piles for laundry. I kid you not. Like we had the purple pile and the red pile and I accidentally put a red sock in with the whites. My dad had pink underwear for a couple weeks because it ran, right? I love my husband. Shh, don't tell anybody. His black underwear. Can't screw that up. You can throw it in with whatever you want, right? Doesn't matter. That and we wash everything in cold nowadays. And you should, because guess what? All the detergents are formulated to wash in cold water. So if you actually use hot water, you're decreasing the effectiveness of your detergent. So stick to the cold, save some electricity, save the world, right? So you don't have to worry about it, right? I can throw a red sock in with his underwear. No one's going to know, right? Because they're black. You're not going to see it, right? Even if it runs, you're not going to see it. It's the more darker color. So in this case, they're already purple, right? Can we stain them red? Yeah, but they're still going to look purple. Maybe just a darker purple. Make sense? Laundry always helps. Or beautiful hair. Okay. So, under the microscope, they're purple. And this doesn't have anything to do with the shape, right? It has to do with having that thick peptidoglycan layer and trapping in the crystal violet iodine. So in contrast, the other result is pink, right? So do they stay purple? No, they're going to get decolorized. And why is that? So, let's go pink. Ooh, that's different, huh? What are we looking at here? So this is a membrane, right? We're used to seeing this. This is peptidoglycan. What's this? Ooh, look, it's telling me. It's an outer membrane. So he doesn't just have one, he's got 2 membranes. And a little bit of peptidoglycan here. So what happens when we go through the steps for him? Well, crystal violet, right? It's going to naturally go where? Inside. Iodine's going to go inside. It's going to do what with the crystal violet? Bind to it, right? We get that crystal violet iodine complex. Okay, what's the next step? Yep, decolorization with usually alcohol, right? So here it comes. Bam. Whoa. What happened? Something's gone. The outer membrane, because what are membranes made out of? Lipids. What does alcohol do to lipids? Destroys them, dissolves them. So, and again, what do you notice in comparison about this peptidoglycan layer as opposed to the other one? Is it? Yeah, it shrunk a little bit. It doesn't have the tectonic acid, and I always think of the teichoic acid. I always think of that as like rebar, right? And there's an engineer who just started building a house in the neighborhood I used to live in. He's awesome. He'll actually talk to my 8-year-old. And he explained to him why it is that they put rebar in concrete. Do you guys know why that is? To reinforce it, right? But he said the other reason is because of the differences in the properties of the 2 things. It helps support it because the concrete changes with temperature, but the rebar doesn't change as much, and so it helps support it that way too. I was like, oh, cool, I didn't know that. Right? But so it helps support it. So, but if we're just putting a little bit of concrete, do we really need the rebar? No, you don't need that extra support. But if we're, doing a whole big thick road, they're definitely going to put rebar, right? So, look. Here. Try and decide. We'll do this. I don't want to add it to my favorites. I just want to open another one. Okay. All right. Gram-positive. Come on. Look at it again. So you got that rebar, that teichoic acid, because what about this layer compared to the other cell's layer? It's thicker. It's thicker. Do you see that now? It's thicker. Teeny. So is it going to be enough to trap it in? No. And that outer membrane's gone, right? It's not staying. It gets rinsed out. These cells would be colorless if you stopped here. So that's why we've got a counter stain, because you'd never see your gram negatives if you didn't do this last step, right? You got to use the safranin, which is a red dye, but this guy's been pretty damaged, right, by this procedure. We've basically removed his poor outer membrane. So he doesn't retain a lot of the red dye. So that's why it looks pink, because a lighter shade of red is actually what we call pink. Cool, huh? So by doing this, how these different layers respond, right, to this procedure, doing it in the correct steps in the correct order, you're going to either get purple, which says thick peptidoglycan layer, or pink, which says thin peptidoglycan outer membrane, if you're talking about bacteria. So those 2 links are there. So you know me, right? You guys will get used to this. I'm the table woman. Make tables for everything. How many of you guys seen this toy? Oh yeah. I wish I still had one. I don't know if you can get them anymore. I had to search the internet for this picture. So this toy has these little plastic blocks on the inside, and they're all these different shapes, and so the little kid's got to match the shape, and it literally just barely fits in that hole, right, those shapes. What they don't usually realize is that these two pieces can pull apart from each other. There's a handle here at the top and the bottom. So once you stick all the pieces in, you can pull the two pieces apart and dump all the blocks out and do it all over again. But most little kids, unless you show them this, don't realize it at first. So they put all the little blocks in, because you usually start like that, right? You give them all the blocks and the ball, and you say, here, have fun, right? And so they put them all in, and then they want to do it again, right? Because it was fun, right? Sure. So what do? They stick their little hand in here, and they grab a block. Then they try to take it out. Can they get it out? No, because that block barely fit in there by itself. Never mind a little hand grasps around it. So then they start screaming until you reason with them to let go of the block, and you get the little hand back out. Then you show them how to open it. But this is the same principle as crystal violet and iodine, right? Crystal violet went in the hole, right? Then iodine went in. The two of them came together, just like the little hand in the block. And so now it's trapped in there. But in the gram stain, what happens to that hole even? It shrinks. So imagine that, right? Little kid puts his hand in, and the hole closes on the hand. You'd really have a screaming kid and a screaming mama at that point. Forget about it. Make sense? All right, so here's your quiz. How do you get that ball out the hole at the top? You take out the sticks. Take out the sticks, right? Clearly the ball went in and then the sticks. And because of those sticks, you can't get it back out. It's an intelligence quiz for you. All right, so let's review these steps. So gram positive, right? We stain it with crystal violet. It's going to be purple, right? Because crystal violet, positively charged, goes in the cell, right? Stains it purple. You add the iodine. What happens when you add the iodine? Still purple. What does the iodine do? Combines with the crystal violet. Okay, now we're going to do alcohol. What's going to happen? Shrinks the peptidoglycan layer. Traps in the crystal violet iodine, so the cells are still purple. Then we're going to stain with safranin, right? It's going to go in, but the cells are still going to look purple. Gram negative. Stain them with crystal violet, right? So they're purple. Add the iodine. Still purple. And what did the iodine do? Combine with the crystal violet. Okay, now we're going to decolorize. And they're going to be clear about why. Yeah, outer membrane gets damaged, right, or removed. And but is that why the purple gets out? The problem with that, too, is not enough peptidoglycan to trap it in. So they lose the outer membrane. They can't trap in the crystal violet, so they're colorless. So we want to see them, though, right? Colorless doesn't count. So then we're going to stain them with safranin, and they're going to be pink, 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 pink. We good? All right. That's both of them side by side.